Hello, everyone. Welcome to another video of our lab helper videos. And in this video, I'm gonna discuss about all the necessary concepts you need to know before jumping into lab 6. So let's start. In the lab 5, we already discussed how our local interrupt that is cleaned works, and it has some registers that is very helpful for us to calculate the real-time clock and use any kind of timer functionalities. In this lab, we also use the M-time register, is basically a 64-bit of register, and that can hold the count of clock cycle passed by the CPU. So I would request you, if you have not seen the lab 5 video, I would strongly suggest you to go through the lab 5 video first, and then come back to the lab 6 videos, because the concepts are, they're all connected, and it will help you to complete the lab 6 easily if you understand the lab 5 concepts. So yeah, in lab 5, we observed that how we can calculate the delay from the real-time clock. The real-time clock is producing 32.768 kilohertz a clock frequency, and from that clock frequency we calculated the time it is passed in our CPU, and from there we observe how we can change the pulses width and control the fan of a servo motor. So in lab 6, we'll also use the local interrupt that is cleaned, and also we're gonna use the M-time register. But before that, we need to understand some other concepts, and I believe you already seen the video of lab 5, and you know how these two primary methods are used for the communication, that is polling and interrupts. So if I want to revisit the concepts of polling and interrupts, polling was basically a concept where the microcontroller monitors all the peripheral devices continuously and looking for a service request flag. On the other hand, interrupts are basically the CPU is remain idle, and if someone seeks any help or need any attention, it informs the CPU, and CPU then go and try to help that peripheral devices. Polling is not a hardware mechanism. It is purely a protocol written in the software, but interrupts is basically a hardware mechanism, because we use our clock frequencies to generate different interrupt signals. So that's why it is a hardware mechanism. Both one of them is polling is serviced by the CPU, and interrupts are serviced by the interrupt handler. So in this lab, we will talk about the interrupt handler more, because that's our point of interest for this lab. And polling occurs at regular intervals, but on the other hand, interrupts occurs at any time. It depends on the call button, as if you remember the analogy from lab 5. In polling, we waste a lot of CPU cycles, but interrupts in the interrupts, we does not waste any CPU cycles. And yeah, that was all for the basic differences between the polling and interrupts. Now, in lab 6, we will go through the detailed concept of handling the interrupts. So how we handle the interrupts, that's the basic question. Microcontrollers handle interrupts through a process that temporarily pauses the current execution flow, right? So as the interrupt name suggests, you are interrupting something, right? So when a microcontroller get an interrupt signal, it temporarily pauses the current execution flow. For example, here, the microcontroller was trying to complete each of these instructions that is inside our user program, and suddenly here it got an interrupt, that is a IO interrupt, and it pauses its execution by saving the program counter, because after completing the interrupt operation, it has to come back again here. So we need to know where we were at previously. So yeah, I mean, the CPU saved the program counter. So program counter basically knows the instruction it needs to execute. And after saving the program counter value, it goes through the interrupt service routine. So yeah, after pausing the current execution flow, it responds to an external, or it can be also internal event, executing a specific function called an interrupt service routine, or ISR, before returning to the main program flow. So it saves the program counter, it executes a specific function that called ISR, or interrupt service routine, and then return to the main program flow. This mechanism allows microcontrollers to deal with asynchronous events efficiently. As you can see here, after done with the interrupt service routine, it goes back again. It went back again to the IO interrupt. I mean, sorry, it went back again to the user program. Now, to complete this lab, we have to understand some of the registers beside the M time register. One of the register is M time compare, and this M time compare, we can use this with M time to implement a timer. So the word timer, I mean, I meant that we are trying to implement a clock. I mean, let's say we want to set a timer for our sleep. So how can we do that? We usually set an alarm on our phone, and after setting the alarm, the time continuously decrease, and when it is 0, it raises an alarm, and we just woke up from the sleep, right? So the same thing, if you want a timer interrupt, you have to set up a timer, or you have to set up an alarm. And how you can do that? You know the current clock cycle from your from the M time register, and we need to set some specific value on the M time compare register. Now, when we are counting up or down in the M time register, if the M time is equal to the M time compare, for example, we collect the current M time value, let's say 1000, and we set the value of M time compare, let's say 2000. And now if the M time is continuously, counting up, at a certain time, we will reach to the value of 2000, and when the M time is equal to M time compare, the CPU gets an interrupt from the board, right? So here, please remember, we are not talking about the second or millisecond or any time. This M time or M time compare, they can only hold the value as a cycle, right? Because we can calculate the time from the cycle. So we have to always think about the cycle. So if I want to add 1 second value in the M time compare, we have to set the value that is equivalent to 1 second. In the last lab, as we see, the 1 second in our SiFive microcontroller is basically 32,768 cycle. So we have to set this value to the M time compare register to store the cycle, and that means it will mean that we are comparing the time, the M time register, just for 1 second. And there are various interrupts connected to our CPU core, but this time we'll only use the MIE, that is machine timer interrupt. This MIE register is generated by the M-time and M-time comp register, straightforward thing. Now, to enable the timer interrupt, we must tweak different bits of MIE register, right? So this MIE register is generated by these two registers. So we have to basically change all of those registers to to get the final interrupt register value. And in addition, we have another control register that is in status, as we used that before. I believe, no, we didn't use it before. So we have another control register that is aim status that can enable or disable the interrupts, including the MIE. So if we observe the aim status register, this is on the right hand side of the table. You can see here the bit 3 is for enabling the interrupt or disabling the interrupt. So we need to use bit 3 of aim status register, and for MI register we need bit 7, that is machine timer interrupt enable. We have to enable this bit to 0 to 1 to make to pass a interrupt signal to our CPU. So in summary, to enable the time interrupts, we need following changes. We have to set bit 7 of MIE register to 1. We have to also set aim status bit, the bit number 3 to 1 to enable the aim status interrupt signal. Now let's go dig deeper into our code. So we have in the library we have some macros here. So macros is nothing but as we already know, macros is just a variable that holds some value. But here our macro is kind of a function that that the preprocessor during the compiling will load or write the value. So unlike the timer registers, the MIE and the aim status registers are not the memory mapped. This is unique from the other registers. We can't directly change the value of MIE and the aim status registers the way we did it previously. We have to access and modify this register's value using a special instruction. And the special instructions are CSRR and CSRW, as you can see here, is read, and for write is W. So you don't have to think much details about these instructions, but just please try to remember if you want to change any value of the MIE or aim status register, you have to use these two macro or these two instruction, that is CSRR and CSRW. So as you can see here, it is read CSR and write CSR. So if you want to write a value, if you want to write a value to this register MIE or aim status, you have to use this write underscore CSR function, and this function take the register address and the value you want to write onto that register. Next, we have another function that is set cycles. So this cycle is basically setting the number of cycles we want to set for compare with the M time register, right? So as we know, we have two registers, that is M time and M time compare. So we are setting the cycle count as fixed cycle count to this M time compare register. And after that, this value will be compared with our M time register. So this is also straightforward. And we are setting the M time compare register to the correct value so that an interrupt is generated right after the 100 millisecond. So in this lab task, our goal is to let's bring the PDF. Yeah. So for lab 6, if we go to your task section, your goal for this lab is to blink a LED at a constant 100 millisecond interval. So so you have to turn on the LED at a constant 100 millisecond of interval. So as a result, when you're turning on the LED, and you have to turn it off again, and the delay you can use when turning on and off the LED is 100 millisecond, and you need to program the timer handler and the interrupt functions to complete this lab. So as we are using a constant 100 millisecond of delay, so we want to compare our current register value with the M time compare register, so that it can generate 100 millisecond of interval, or it can generate a delay of 100 millisecond. And if the time 100 millisecond passed, it will directly our interrupt handler will directly pass an interrupt signal to the CPU to tell that whatever you're doing, it was doing actually turning on the LED. Please stop, and then wait 100 millisecond, and then you can do whatever you was doing previously, right? So set cycle is basically set the register value of our M time compare register, and we have another function in the interrupt.c file, that is enable timer interrupt function. So in this function, this is a void function, and you can see here we are modifying the MIE register, and what we are doing here, we are collecting the data from the MIE register. So we know how it looks like inside of the MIE register, and we know we want to change the bit 7. So this variable MIE might bit has the value of 7. If we go to our library file, you can see how our the machine mode timer enable bit is 7. So we are using this variable here, and what we are doing, we are shifting the 1 to that many position, and just simply doing the OR. So I believe you're already familiar with this operation. It is pretty much straightforward. We are just reading the data from the register, and we are setting the bit 7 to 1, as you can see. So it was the most important part for this lab to understand. And now if we go through our code, so all the codes are already done for you, like turning on the LED. What you have to do, you have to complete these 3 functions. That is, you have to implement your timer handler, you have to implement the enable interrupt function, and you have to disable the interrupt function. So as we already go through our slides, we know we also we just not only have to set bit 7 to 1 in MIA register. We have to also modify the M status register, right? Because this M status and MIA register, they both works together to generate the interrupt. So in this function, like enable and disable interrupt, you have to turn on these bits to 1 in this enable interrupt function, and you have to turn off these bits to disable interrupt function. So you can easily do that by if you follow this line of code, it should be pretty easy for you to complete this 2 function. And for this function, that is timer handler, so in this timer handler function, you have to set you have to set up the timer. Like for our task here in this lab, we have asked to set an interrupt for 100 millisecond. So what you have to do, you have to collect you have to collect the current clock cycle and add 100 millisecond with it. And so you can't directly add the millisecond with this function. So you have to use this, because you have to use these set cycles, right? I mean, so first you have to use the get cycles and add the correct cycle count number for 100 millisecond. And after adding that, you can complete this timer handler function. And I mean, if you're done with these three functions, you should ready to observe the blinking of your LEDs in 100 millisecond of interval. Now I want to give you one more hint, that is that timer handler function. Let me bring the picture again. Let me bring the code again. Give me 1 second. Yeah. So in your timer handler function, you have to set a variable where you want to keep your you want to calculate the correct cycles count for 100 millisecond, and you have to add it with the existing cycle, because the time is always counting in the M time register. And once you calculate that, you can use again this set cycles to set that value inside this M time comp register. And finally, this timer handler will call in your main function to generate that interrupt. And based on that interrupt, your LED will blink in 100 millisecond of interval. I hope it will help you to complete your code and the concept. Yeah, that's all. Thank you so much.